project EW2 project fast acting resistive hot plate with control and display. Today we are going to explain you about it. Benefits: fast heating, precise temperature control, real time temperature feedback and energy efficiency, increased productivity and cost effective. These are some of the benefits that we kept in mind before making this project. Application: it can be used a lot of where, like laboratory work, cooking, industrial processes. And the things that we invested in this are valuable tools for its efficiency and productivity, such as we used various ICs and like our resistive plate, etc., essentials for achieving goals and quickly and reliable. So we also did some study work before making this project, like studying some papers and all, and we got to know about various new things that helped us a lot for making this project. And some of them were this diagram, which is like the essence of the project. The whole basic of the project is this: there will be control system, there will be heating element, and there will be feedback. One of the major working principle of our project is very similar to the electric iron that we use. In electric iron there is a bimetallic plate, but we have used a LM35 temperature sensor. That's an analog temperature sensor which gives back the feedback, and we control the temperature of our circuit according to it. This is the basic block diagram of our project. There is a temperature control unit where we can set our temperature accordingly, and it then starts heating the heating element. There is a temperature sensor connected to the heating element, which gives the feedback to the temperature control logic. So if the current temperature exceeds the desired temperature, then it starts the circuit, and when the temperature comes down, it again starts to heat it. Hence it creates a kind of oscillator around the desired temperature. So the components that we used in this are LM35 temperature sensor, which is an analog temperature sensor. It works on the principle of capacitance. Heating element that we used is a aluminum resistive plate. Arduino just for display purpose. Potentiometer for setting up the desired temperature. A comparator for comparing the feedback of the current temperature and the desired temperature. A MOSFET for shutting down the circuit on certain difference of voltages. Diodes and relays. So this is our circuit diagram. This is our main circuit diagram, in which you can see there is a MOSFET and there is a relay, and this is a temperature sensor, and from here potentiometer we can set our desired temperature, and this shows current temperature, and it is a comparator. When the current temperature exceeds the desired temperature, this comparator shows zero output, which turns it off. Zero voltage goes to this MOSFET, which turns it off, and zero current flows through this relay, hence relay turns off. So this is our heating circuit which turns off, and when again temperature goes below the desired temperature, it again turns on, which turns on this MOSFET, which allows current to flow through this branch, which again turns on the relay, and this heating circuit turns on, and this is our heating element which starts to heat up. This is a LM317 circuit which we used to maintain 1.4 volt across our potentiometer, because that was the limit of our temperature. LM317 is an IC that works on the is a voltage controller. It works on the principle of variable resistance and feedback using op-amp. These are some of the calculations. Like these are the calculations of the resistance that we need to use across the relay in parallel. We need this because relay keeps turning on and off, so we need to maintain a constant resistance also in the MOSFET branch. So we used a resistance such that whenever the relay is on or off, the constant resistance we try to maintain. So according to our calculation, relay resistance was 100 ohm, and we used a resistor of 66 ohm. So whenever relay is on, the equivalent parallel resistance comes out to be nearly 67 ohm, and otherwise it's 66 ohm. Hence it maintains a constant resistance in the branch. So this is basic working principle of LM317 voltage regulator IC. This is the formula through which we can calculate what is the constant regulatory voltage that we want to keep across through the adjust pin of the IC, and it helped it a lot. We used the value R1 is 1 kilo ohm and R2 equal to 120 ohm. This helped us to maintain a constant output voltage of 1.4 volt. What is the basic intuition of the working of the circuit? This is very important for understanding what the circuit is doing and how it's working, and it's very simple. We are using a LM35 temperature sensor. It's a analog temperature sensor, and its voltage versus temperature characteristics comes out to be like this. Voltage is 10 times temperature in degrees Celsius millivolt. We set a desired voltage, and we also get some feedback from the LM35. We compare both of them, and we outputs it to MOSFET, which controls the heating element. Some analysis that we did, this was the temperature sweep of LM35. We saw that at certain temperature, at temperature equal to 70 degree, our circuit turned on, and it kept turned on for a long time at 5 volt, which will turn on the relay and the heating will start. And at temperature, low temperature, there was 0 voltage, hence our circuit will be off. And we also calculated the LM317 voltage transfer DC transfer characteristic, which we can show that at a higher voltage it is constantly maintaining 1.4 volt. We tested our circuit and we found very satisfactory results. We gave our control logic 7 volt DC and our heating element 220 volt AC, and we set temperature 100 degree, and we observed that in around 1 minute only it reached from 30 degrees Celsius to 100 degrees Celsius, and it also boiled the water. And there was limitation of LM35 that its temperature range is around 150 degrees Celsius, so we advise not to use it above 130 degrees Celsius, otherwise it will melt. But the challenges that we faced include, one of the main challenge was the temperature sensor itself, because LM35 is we wanted an analog temperature sensor whose temperature versus voltage characteristic must be linear and it must be fast, but LM35 fulfills all the requirements except that it is very slow. So while using it, first of all the temperature shoots up and after that it comes down and then it oscillates, so it's kind of a slow. But you can avoid this challenge by using some other efficient temperature sensor that will help you a lot. And another very challenging thing that we faced was connecting our temperature sensors to the circuit, because when we heat the circuit there are most of the adhesives don't work properly, so we advise you to purchase a high temperature resistance tape, which would help you a lot. So in conclusion, we found out that the problem statement that we were given, we tried to work on it very nicely, and up to some extent we did it perfectly, and our circuit is also working perfectly. Thank you. So from here we can set desired temperature. Currently I am setting it to 100 degrees Celsius so that we can show boiling the water. And here is also our current temperature, like at what temperature this metallic plate currently is. It is working on a temperature feedback loop. Here is our temperature sensor. It will give feedback to the internal circuitry, which will control the temperature. Now you can see that currently temperature is increasing with a good rate. Currently we have reached 60 degrees Celsius. (65 degrees Celsius), 70 degrees Celsius, 76, around 80, 55. We are around 90. We crossed 90. we are very close to reaching our desired temperature. Once it reaches the desired temperature, it will stop heating. Like you can see, LED has stopped glowing. Now we will pour some water on the plate and we'll show that it will be boiled. See, it boiled up, which means it has already crossed 100 degrees Celsius, which was our desired thing. Now it will constant on 100 for some time because LED is not glowing, and once it will start reducing, it will again turn on. So now the temperature has reduced from 100 degrees, so it again starts to heat. So it works on this oscillation principle. And this is one overview of our internal circuitry we have used in relay. And this is from where we are adjusting. This is Arduino for display. This is our OLED display. Thank you.